last time I tried to do this, I failed. So, but let me, wait, it's saying dot, dot, dot. Normally it, oh, am I the only host? No, I'm not a co-host.
Yes, you are the host.
Oh, okay. I only wanted to be a co-host. This is a lot of responsibility. Okay. I think maybe we're recording. I promised Sander I would record the talk, but worst case, I'll just send him the slides. And, yeah. Okay.
All right. You're very happy to have Bruno from Jussieu Institute of Mathematics talking about the rank spectral sequence for algebraic K theory.
Thank you very much. I would like to give a caveat. First, Jeremy kindly invited me to give this talk here, but this is some work I have done 5 years ago, about 5 years ago, and I haven't worked on it again until recently. And second thing, I'm not a topologist, so I struggled a lot to work on this. So please bear with me if anything is a bit fuzzy, or but please ask questions. So this is something which developed from a work of Quillen, which was, yes, his big theorem that the K groups of integers of number fields are finitely generated Abelian groups. That's in the basic lecture notes on algebraic K theory. And I will give, so I don't know why. Yes, I'll give a sketch of his proof. He does this. So first he applies, I think it's Whitehead's theorem to reduce from homotopy to homology. So he thinks of the K groups as the homotopy groups of the Q construction on the category of finitely generated projective modules on A. And then this is a homotopy, commutative and associative H space. So he wants to show that its homology groups are finitely generated. Then the second step is to filter this category QP of A by rank. So you call Qn the full subcategory of finitely generated projective modules of rank at most n. And then he constructs long exact sequences. So you can map the homology of Qn minus 1 to the homology of Qn. As usual, homology of a category means homology of its classifying space. And then there are third terms which are described here by this direct sum. So term of the direct sum is the homology of the automorphism of this particular projective module, P alpha, with values in the Steinberg module associated to P alpha, which means you tensor with the field of fractions of A. So you get an F vector space. And I will go back to the Steinberg module later. You don't need to worry about it now. And alpha goes over isomorphism classes of these projective A modules. And since A is a ring of integers, it's a Dedekind domain, and its class group is finite. So this direct sum is finite. So so Quillen reduces to showing that each individual homology group with values in the Steinberg module is finitely generated. And then to do that, you can replace GL of P alpha by a torsion-free subgroup of finite index. And then you can apply a theorem of Borel-Serre, which says that the homology of gamma with values in this Steinberg module is canonically isomorphic to its cohomology in another degree. L is a certain integer depending on gamma. That's a duality which was I guess, independently found by Bierrig-Ekman, but this is a special case of Bierrig-Ekman duality. And then, sorry?
So next Monday, I'm having an exam, so I can meet earlier.
Daniel, you're not
needs to
muted.
mute themselves.
Was it a question?
No. Oh, one comment though. I think Borel-Serre duality, you need to twist with something for GL. Like I think you stated it correctly for SL, but like for GLN-Z, when n is even, you need to tensor with the determinant representation.
That's possible, yes.
Yeah, but I mean, let's say the proof works, but yeah, there's a...
Yes, maybe it's sloppy. No, Quillen is never sloppy, but I remember that to use Raghunathan's theorem, that's where he reduces to SL. So well, I don't know, but in any case, this argument works.
Oh yeah, if you're in a finite index subgroup, it's probably contained in SL, and then Steinberg is the dualizing module once you're in.
You have the units of A, which are not finite group, so I don't know. But I'm just sketching the proof, and I'm not going to use this this part 3 in the sequel. So it's just for information. It's a description of the proof. But there's a comment about this proof, which is there's a simpler way, but it was not available when Quillen made his proof. And this simpler way is to think of K groups as homotopy groups of the plus construction. Then you don't have this shift and pi I plus 1, but it doesn't matter. So then, by the same argument, it's sufficient to show that the homology of BGL of A plus is finitely generated. And this is here the limit of the homology of the groups GLN of A. And the point is Van der Kallen's theorem, which is it's a stability theorem, which says that when I is fixed and you increase n, then the stabilization maps eventually become isomorphisms. So using this argument, you can avoid the Borel-Serre duality. So it looks like it's a bit complicated, but I would like to explain that this argument of Quillen remains interesting. So the first remark, yes. So I've put some links that you cannot click on them, but Jeremy I sent the slides to Jeremy. So if you like, you can click on them on the file. So in any case, I'm going to talk about basically 3 preprints. First one is, first observation is that the long exact sequences of Quillen, in fact, yield an exact couple and therefore a spectral sequence. So let me go back to the sequence. That's the sequences star. So just look at them and you see that they underlie an exact couple. So Quillen's construction gives more than his argument. It gives a spectral sequence. And you could use this spectral sequence for more results. So initially, I thought of this. There's something which is unsatisfactory in arithmetic geometry, which is concerning K groups of integers. There are 3 different theorems. First one is their finite generation. And then the 2 others are first a computation of their rank by Borel. And then a relationship between regulators associated to these K groups and the special values of the Dedekind zeta function of A. That's also a theorem of Borel. And these things have 3 separate proofs, which means maybe the 2 proofs of Borel are related, but definitely Borel doesn't need finite generation. He computes the dimension of this K group tensor R. While for K1 and K0, these are classical theorems of algebraic normal theory. This is the finite generation of the ring of integers and finiteness of the class group. And then there's a single proof which proves everything at the same time, which is finite generation, rank, and the relation between the regulator and the value of the zeta function at s equals 0. So it's unsatisfactory that for hierarchical groups, you have 3 different proofs, and one would like to have one unified proof. And I had the dream that maybe using this spectral sequence, one could get to such a proof. But so far, it's still a dream. I'm not claiming anything. But still, that's one reason I wanted to use this, to study this spectral sequence. So to get to it, I would like to explain how Quillen proves construct these long exact sequences. So here's his proof. So you look at the inclusion functor of Qn minus 1 to Qn. I remind you that Qn is the full subcategory of the Q construction made of projective modules of rank at most n. And then when you have functor between 2 categories, if you look at Gabriel Zisman's book on calculus of fractions and so on, they construct a spectral sequence which converges to the homology of the left category. So here, Qn minus 1. So Quillen does that. And then the miracle of the Q construction is that you have to look at the so-called homotopy fibers of this functor W. So it means you take an object in Qn, and then you look at this W down arrow P. I'm using MacLane's comma construction. So it's explained here. This is sometimes it's written W over P. So the objects are maps from P prime to P via W for P prime in Qn minus 1. And morphisms are just commutative triangles. In this case, there's no mystery. It's a fully faithful functor. So this is the comma construction. And then when you look at the definition of the Q construction, you see that this category W down arrow P is just the poset of admissible layers in P. So that means P0, P1, and P0 is contained in P1 inside P, and the quotient P1 over P0 is torsion free. And so it's almost a tautology that the classifying space of this category is the suspension of the Tits building of P extended to the quotient field of A. This implies that a spectral sequence of Gabriel-Zisman degenerates at E2, and this gives these long exact sequences star. So it's not very nice because I get an exact couple, I get a spectral sequence by piling up degenerating spectral sequences. Can we understand this a little better? And then for that, the next idea is to think of the map from BQN minus 1 to BQN not as a fibration, but because that's what Quillen does in effect, but as a cofibration, and then you get naturally long exact sequences of relative homology, and you get very naturally a spectral sequence, and it's easier to study. And there's an argument of Pierre Vogel, which explains that the exact sequences obtained by this technique are the same as the ones of Quillen. So it's good. Okay, so here's the idea to do that. This functor from Qn minus 1 to Qn is a cellular functor. So a cellular functor is, in another word, it's the same as a sieve, but I want to think of it in a different way than sieves. So a functor from a category C to a category D is cellular if it is fully faithful first, and then I cannot map an object of D to an object of C unless it is already in C. So there are no morphisms from object of D minus C to objects of C. So then to explain the next theorem, I need some notation. If I have any functor from C to D between two categories, I write F sub T for a functor from D to cat, that's the category of small categories, is the functor which sends an object D to the comma construction T, but down arrow D. So that's one thing. And the second thing is what is called Grothendieck's construction. So if I have a functor from a category D to cat, then I can construct a new category, which is D integral F. And I will just describe its objects. Objects are pairs of an object of D, and then an object X of F of small d. And then morphisms are more or less obvious. If you have a morphism from D to D prime, then I have a functor from F of D to F of D prime, and a map from Dx to D prime X prime will be a map from D to D prime, and a map from F of D of X to X prime. So in any case, this Grothendieck construction is naturally F. So you get an augmentation from this Grothendieck construction to D by mapping F to the constant functor, which sends every object to the single category, to the 1 point category. And then the main technical theorem is a homotopic co-Cartesian theorem. So there's a diagram like this, which is naturally commutative and homotopy co-Cartesian. On the right, you have this functor from C to D that I want to understand, which is supposed to be cellular. And on the left, I have this augmentation I was mentioning. Here on the bottom, there's the inclusion of D minus C into D. And on the top, this P is a projection functor, which is because you can send this D minus C integral ft to D integral ft. And if you think of the definition, you find a canonical functor to C. So that's what is true. And then once you have such a homotopy co-Cartesian diagram, you get a long exact sequence, a long Mayer-Vietoris exact sequence of homology. And I prefer to write it in terms of the homotopy fiber of this, sorry, I'm using my finger, homotopy fiber of this epsilon. So I will not explain the notation in detail, but this gives a long exact sequence of this form. You have hi of C, hi of D, and it recognizes the third term. That's how we construct the spectral sequence. So now in the application, I take an integral scheme X, and as an ambient category, I take the Q construction on the category of coherent, that should be X sheaves of OX modules. And then inside this Q construction, I have the full category made of coherent sheaves which are torsion-free. And by Quillen's resolution theorem, this is a weak equivalence on the classifying spaces. So I'm going to work with the left category, the torsion-free category. And then inside, I take as before Qn as the full subcategory of torsion-free sheaves of rank at most n. And then in the above, I take C equals Qn minus 1 and D equals Qn. So this is Qn minus 1, this is Qn. I have the third term. And then when you go back through the definition of these things, you find that the third term has the form of this direct sum, and you get the rank spectral sequence for the Q construction, which is like this. So it converges to the homology of the this gives, when you take homotopy groups, you get the so-called K prime groups of X. And the one term is sum of homologies of automorphisms of these sheaves with values. So here I'm a little more precise in the reduced Steinberg module of the generic fiber of E alpha. The reduced Steinberg module, I will explain it later, but let's say that when the rank is at least 3, it's the same as the Steinberg module. And when the rank is 2, then it's a little different. And for 0 and 1, it's just Z. So, and if you want to use this spectral sequence, the first thing to understand is its D1 differentials. To explain how it could be used, let me take an example, which is, suppose that my X is proper over a finite field K, then these automorphisms of these torsion-free sheaves are finite, and therefore the E1 terms are torsion for Q bigger than 0. So if you tensor with Q, everything disappears except for Q equals 0, so you have only one row. So what you have to compute is this D1 differential on, at least on that row. And maybe it could be used to compute the ranks of the homology of the Q construction, and then potentially to get the ranks of K prime of X by the theorem of Cartan and Serre. And so far, this is still an open question. But let me go on with the problem. So I will do, just to say things quickly, a student of mine computed these D1 differentials in terms of, in particular, universal modular symbols. So I'm going to explain these universal modular symbols first. And before that, I will go back to the Steinberg module. So let me define it properly. So if I have a vector space of dimension n over field K, then its Tits building is the simplified complex whose vertices are the proper subspaces of V. So proper means different from 0 and V. And the simplices are the flags. And then the Solomon-Tits theorem tells you that T of V has the homotopy type of bouquet of n-2 spheres. And therefore, it has only 2 non-zero homology groups. That's Z, because it's connected, and the top one, which is the Steinberg module, which GL of V acts on T of V, therefore it acts on Steinberg of V. And then the reduced Steinberg module is defined like this. If n is bigger than 2, this is just the Steinberg module. If n equals 0 or 1, it's Z. And if n equals 2, then you see n-2 is 0. And there's an augmentation of Steinberg of V to Z. And this is the kernel of this augmentation map. For n equals 0, the Tits building is very easy to understand. It's a discrete space, which is the discrete space of defined by P1 of K, a set of lines a set of points of the projective space. And then this epsilon sends each line of Steinberg of V to 1. Okay, so that's the reduced Steinberg module. And then I come to the universal modular symbols, which are defined by Ash and Rudolph in the paper of the 70s, I think. So to define them, I take a sequence of non-zero vectors of V. And with this Q, I can define a simplicial map. Okay, so delta n minus 1 is the n minus 1 simplex viewed as a simplicial complex. SD is the first barycentric subdivision, partially the boundary of this. And then this map phi q sends each vertex in n minus 1 to the subspace of V generated by the VI's for I in this subset capital I. And Ash-Rudolph define the universal modular symbol associated to Q as the image of the fundamental class in Steinberg of V, where the fundamental class corresponds to the canonical orientation of SD of delta n minus 1, which is fine for n bigger than 2, but for n equals 2, there's a problem because this space is disconnected. So the solution is to take for zeta the class of, oops, one parenthesis missing, of 1 minus 0 in H0 of delta 1, and then to make the same definition. And then we get the universal modular symbol defined for all n greater than or equal to 2. And here's a list of its properties. So first, it's antisymmetric in V0, Vn. Then it's multi-homogeneous of degree 0. Then it vanishes if the vectors V0, Vn are linearly dependent. And then there's this simplicial identity, which is, if I take, actually, it was V1 Vn or V0 Vn minus 1. But if I take one more vector, and if these n minus 1 vectors are all non-zero, then this alternating sum is 0. And then finally, there's an action of GL of V on this, which respects the modular symbol, like this. And then the last thing is that these universal modular symbols generate the reduced Steiner module. There's another kind of generators of the Steinberg module, which were defined by Lee and Sharba. I'm not sure I pronounced Sharba correctly. But it can be shown, this is shown in this paper, that the symbols of Lee Sharba coincide with these universal modular symbols. And as a corollary, the universal modular symbols actually present Steinberg, the reduced Steinberg module for the relations from A to D. Okay, so then, well, that's not essential, but this is something which is used in phase thesis. So let me explain how you can hype up the Ash-Rudolph construction. Are there any questions so far? Then I go on. So let me take a Noetherian domain and torsion-free, finitely generated A module of rank n. I want to explain the Ash-Rudolph construction as a map of posets. That's what is here. So let me explain what I'm going to do. If I have a submodule of this torsion-free module, then we say that it's pure if the quotient is torsion-free. And if it's not pure, then I can saturate it. I can create a slightly larger submodule, nsat, which is pure. It's just what is written here. It's the kernel of a map M to M mod n, and then a quotient M mod n by its torsion subgroup. So then, given this M, let me define G of M as the partially ordered set of pure submodules of M, which are different from 0 and M. And then, on the other hand, let me consider E of M, which is the simplest complex of finite non-empty subsets of M, such that the rank of the submodule they generate is less than N. I'm just basically copying what Ash and Rudolph do. And then, well, you can interpret what they do as a map, as a non-decreasing map from the poset of simplices of E of M to G of M. And then, so what's that good for? Well, first of all, G of M doesn't see really this M and this ring A. It only sees its field of fractions. So it's the same as G of V, where V is the extension of scalars to the field of fractions. And then if I'm over K, then it's basically a tautology that the classifying space of G of V, viewed as a simplicial complex, is the Tits building of V. And then the point is that this Ash-Rudolph map that I wrote before is a homotopy equivalence. And the proof is almost trivial, because you think of AR as a functor, thinking of partially ordered sets as categories, and then you apply Quillen's theorem A. So it means to apply Quillen's theorem A, I take an object in the target and I look at its homotopy fiber, and then you compute that the homotopy fiber is the PO set of finite subset of n minus 0, which, well, that's all. And this partially ordered set is contractible. So proof is finished. And then from this, you deduce also very easily the Solomon-Tits theorem, because we take A equals K. And then on the one hand, it's easy to see that this simplicial complex E of V is n minus 3 connected. It's the one which is on the left here. And on the other hand, the Tits building has dimension less than n minus 2. And there's a lemma that if you have a space which is n minus 3 connected and a dimension at most n minus 2, then it's a bouquet of n minus 2 spheres. Okay, so then the last thing I want to explain, and this is going to be very sketchy, is what Feysan does to compute this differential D1 in the rank spectral sequence. So this differential looks like this. It goes from this direct sum for modules of rank P to the same direct sum for modules of rank P minus 1. And here it's HQ, and here it's HQ also. So the first step is that for E of rank P, he defines a morphism from the reduced Steinberg module of E to the direct sum of the reduced Steinberg modules of E prime for maps from E prime to E, where E prime is of rank 1 less, like here, and E prime to E is a morphism in the Q construction. And this morphism is obtained by a categorical method. So some computations with the way the spectral sequence is constructed, because the strategy to compute these D1 differentials was to be as stupid as possible, look at the construction of the spectral sequence, and then if you follow everything, then you should be able to describe this D1 differential. That's That's all there is to it, except that it becomes extremely complicated.
I have a question.
Yes.
Of the Steinberg E prime as like Steinberg E prime tensor, Steinberg of like something rank 1. So just like tensor, or like is there a way of thinking of this as like some coalgebra structure on Steinberg? Like, is there a map from so here you're mapping it to things that are ranked like E prime is 1 lower rank than E.
Exactly.
If you were, is there a similar map that would go to something, where E prime is rank 5 lower, but then maybe there would be a tensor Steinberg 5 term that would be there?
You can iterate this, of course. So I don't know.
I get, yeah, but then if you, I don't, okay.
Yes, actually, when I prepared this talk, I thought this is a little baffling because one would like to see these maps without this completely abstract construction. So I tried to think of a way to describe these maps directly. And I came to this. It's the next slide, if it wants to go. Yes. So you have to understand that in the Q construction of Quillen, there are 2 types of morphisms from E prime to E. There are admissible monomorphisms, and you want the quotient to be also torsion-free, but in any case, at this level, you can work on the function field of X. You can imagine that X is the spectrum of the field. And then there are epimorphisms. And then, so here's my attempt to describe these maps concretely. I would like to try to define a map from the Tits building of E to the suspension of the Tits building of E prime. And as I said, I reduce to the case where K is a field. And in fact, there's a pretty obvious map, which is like this. We can think of the suspension of T of E prime as chains of subspace of E prime, so V0 Vp, where you put the condition that V0 Vp cannot be V0 cannot be 0 at the same time as Vp is E prime. That's one description which is in Quillen's paper of the suspension. So I want to get a map from T of E described as before to the sigma of T of E prime described like this. And the obvious try is to take a chain in E and to take its intersection with E prime. And it works because you cannot have V0 intersection E prime equals 0 and Vp intersection E prime equals E prime at the same time. Because if you have the second one, then it implies that E prime is contained in Vp, but E prime has codimension 1. And Vp is not equal to E. So we must have E prime equals Vp. And therefore, V0 intersection E prime is V0, which is non-zero. And then in case I of epimorphism, it's the dual procedure. You project to E prime, and it also works. So here are some candidates for sans morphisms, but I don't know if they are sans morphisms. And it could probably be checked by the next slide, but I haven't done it. So the next slide is a bit surprising. Here's his, well, it's not his main theorem, but it's the main step towards his main theorem, which is to compute this map 3 star on universal modular symbols. Because if you think of what I just described, it's not even obvious that this lands into the direct sum. A priori, it lands into the product if what I described are sums morphisms. But this says that in particular, it lands into the direct sum. So he says this. You take n, I think it should be V1 Vn. So take V1 Vn, n linear independent vectors in E. And then you look at the modular symbol V1 Vn in the reduced Steinberg module. And its image in Steinberg of E prime. So remember that E prime maps to E by the Quillen construction. So if this map is a monomorphism, the image is 0 if E prime is not of the form the subspace generated by all vectors except for 1. And in the latter case, so if E prime is generated by all VI's except VI, all VJ's except VI, then it is the corresponding symbol with a certain sign. And in the case of an epimorphism, it's the same story. So if you don't get what is generated by some subvectors, then you get 0. And in the other case, you get the corresponding symbol, but with a sign which is minus the sign above. And that's for n at least equal to 3. And if n is at most 2, he gets something similar, but with a definition of his of extended modular symbols, where in an extended modular symbol, some of the vectors are allowed to be 0. And then, well, here's the only thing I can say for the D1 differential. So I wanted to say, when using this proposition, probably one can check whether what I proposed before is his construction or not. But I don't know. And then to finish, it's complicated, but what he does is to extend the formulas of the previous slides to chain complexes which compute the homology of the automorphism groups with values in the Steinberg, reduced Steinberg modules. And that's complicated formulas, but they are completely explicit. And I think, yes, that's all. So thank you for your attention.
Thank you very much. I clap on behalf of everyone.